A container is filled with 3 moles of nitrogen gas, 2 moles of oxygen gas, and 5 moles of chlorine gas. If the total pressure in the container is 550 kilopascals, determine the partial pressure of each gas. Sometimes students have issues with partial pressure problems because there's not just one type. They could come in a variety of formats. But the main idea behind any partial pressure problem is that it is parts over whole. And really, it's a ratio of parts over wholes. Some people use the mole fraction concept. Some people just use ratios, which is really the mole fraction concept spread over different dimensions. But if the total pressure in a system is something and you have to find the partial pressure of a part of that system, you can do that by setting up ratios. So we want to find the partial pressure of each gas. As far as how it appears, partial pressure is usually written as a capital P with a subscript for the gas formula. So the partial pressure of nitrogen would be P subscript N2. The partial pressure of oxygen would be P subscript O2. And the partial pressure of chlorine would be P subscript Cl2. Make sure that you know which gases are diatomic, and in standard conditions they appear in pairs. Nitrogen, oxygen, and chlorine are all diatomic gases, so they do need that little 2. Let's first determine the partial pressure of nitrogen. So we know the number of moles of nitrogen there are. There are 3 moles of nitrogen. And we're going to divide those 3 moles in a ratio by how many total moles there are. So remember we said it is parts over whole. When we zoom in on the part of the system that is nitrogen, there are 3 moles of nitrogen and a total of 10 moles. And usually I abbreviate total as a capital T, just to save space. So 3 moles out of a total of 10 moles. If you're wondering where I got the 10 moles, there are 3 moles of nitrogen, 2 moles of oxygen, and 5 moles of chlorine gas. The sum of those would be 10. What this effectively says is that 30% of the moles that are present of the gases come from nitrogen. One of the main ideas of partial pressures is that partial pressure is closely related to partial volume and also moles, which is N. So we don't have the total volume of this system because that's not what the problem is talking about, but 30% of the volume is nitrogen, 30% of the pressure is nitrogen, and 30% of the moles is nitrogen. But 30% of the mass is not necessarily nitrogen. The mole concept does not transfer to mass. So continuing with our ratio, if we know that we have the parts over wholes, the ratio can be completed by determining the Pn2, which we're finding that's our variable, divided by the whole pressure, which would be 550. You can cross multiply, or you can turn the 3 moles over 10 moles into 30% and do 0.3 times 550. But what you're basically trying to determine is what is 30% of 550, or 550 times 3 divided by 10 equals what is the partial pressure of nitrogen? The partial pressure of nitrogen is 165 kilopascals. Ensure that you have units that match. Sometimes, if you're in a class like mine, the teacher may ask that you convert. If this question had asked determine the partial pressure of each gas in ATM, you would have to convert from kilopascals to ATM. Let's determine the partial pressure of oxygen. Oxygen, as a part over whole idea, would be 2 moles of O2 divided by the still 10 moles total. And that is equal to the unknown partial pressure of oxygen, so we're just going to leave it as a variable of P subscript O2, over the total pressure, which we said is 550 kilopascals. Using the same principle of cross multiplication and basic algebra concepts, you can determine easily that the partial pressure of oxygen is 110 kilopascals. And that should make a lot of sense, thinking about it logically, because 2 is a fifth of 10, and 110 is a fifth of 550. It's just a ratio. And the last one, which is determining the partial pressure of chlorine, we have 5 moles of chlorine gas out of the 10 moles total. And a lot of people are going to be able to look at this immediately and figure out, well, 5 is half of 10, therefore half of 550 should be the partial pressure of chlorine, which would be correct. So the partial pressure of Cl2 divided by the total pressure of 550 gives you a partial pressure of chlorine gas of 275. Kilopascals. Now look at all the answers, 165, 110, and 275 kilopascals. The sum of all the partial pressures should equal the total pressure. 72% of the volume of a scuba tank is nitrogen gas, and the rest is oxygen. The total volume is 11 liters. Determine the total pressure if the partial pressure of nitrogen is 2088 kilopascals, and then determine the volume of both nitrogen and oxygen in this mixture. And those would be partial volumes because we know the total volume is 11. One of the easiest ways to start a problem like this is to get things listed out as simply as you can. So I'm going to put nitrogen here, and the nitrogen gas makes up 72% of the volume. The oxygen gas makes up the rest, and the rest, as you know, would be 28% because percentages have to add up to 100%. Sometimes percentages are not explicitly given. If there are 2 gases in a system and one gas's percentage is given, then you can figure out the other one by subtracting the given percentage from 100. If you were to draw out a diagram of what this would look like a cross-section of the volume of this scuba tank unmixed, it would be 72% nitrogen and 28% oxygen. Of course, the gases will be mixed and they will not be settled like this, but it helps to think about this, especially when you are given masses rather than moles or percentages, and that'll be in a later example. So the partial pressure of nitrogen is given to us, and here's how we set up our parts over wholes analogy. And I'll separate it with a bar right here. Dealing just with nitrogen right now, we know that 72% of the volume is nitrogen, and of course the total volume would be 100%. 100% comma T for total. That's just my notation. You or your class may have a different way of doing it. You may use the mole fraction concept, which is related to this, but there's no mention of moles, but the idea is the same. 72% nitrogen over 100% total equals, we do not know the total pressure. That is actually what we are finding in this case. It says determine the total pressure, but we do know the partial pressure of nitrogen, and that would be 2088 kilopascals. That is the P subscript into the partial pressure of nitrogen. Cross multiplication and just general logic would show you that if 72% of the volume is nitrogen, then 2088 is 72% of some number. And with some cross multiplication, you can figure out that the total pressure, and I guess I'll go back to the correct color, the total pressure equals about 2,900 kPa. Although this problem is not asking us for the partial pressure of oxygen, the partial pressure of oxygen would be the difference between this number and this number. Part B, how many liters of nitrogen gas are in this pressurized mixture, and how many liters of oxygen are in this pressurized mixture. So that was part A at the top. Part B, we are going to first figure out nitrogen with the part over whole. We do know that it's 72% nitrogen out of 100% total. This is our part over whole still. We do not know how many liters of nitrogen there are. So I'm going to put V subscript N2 for volume of nitrogen. That's our variable, but we do know that the total volume is 11 liters. Cross multiply, and you get the total volume of nitrogen as 7.92 liters. There are two ways to get the partial volume in liters for oxygen. You could do 11 minus 7.92 to get 3.08 liters of oxygen, or you could set this problem up again by replacing 72 with 28, but the work is going to be the same. That concludes the first two examples of partial pressure. They can come in multiple different types. One of the most important things to do is remember that it is parts over whole, and if you set up a ratio or a mole fraction, make sure that you have all the information written out before you begin, because sometimes it'll ask you about the partial pressure or partial volume or moles of something that is not explicitly given numerically.